In this video, we're looking at the small sample size case when comparing two population means using hypothesis testing. We know the 7 steps of hypothesis testing. We already looked at the large sample case here, so I don't really want to go through those 7 steps again because I think you can look back and see those. And when we look at these sample problems, the actual problems where we work out the mechanics of each problem and solve problems, you'll see how all that's done, and nothing has changed really there. The main thing that changes that we want to address is the issue of the test stat formula when you have a small sample size problem and the degrees of freedom that are going to be used for the t-distribution in those instances. So I want to cover the scenarios. There's actually going to be 3 scenarios that we need to worry about. So let's talk about those 3 scenarios. Scenario 1 is where the standard deviation, or the population variances, I should say, are assumed to be the same. If that's the case, then your test stat formula basically turns out to be t equals to x bar 1 minus x bar 2 minus d naught, the difference you find in the null hypothesis, many times that's 0, right? Divided by the standard error for this estimator under the assumption that these guys are equal, right? That the population variances are equal. So that's going to be SP squared over N1 plus SP squared over N2. So that's your test stat formula. And the degrees of freedom in that scenario, the degrees of freedom for the t-value is going to be N1 plus N2 minus 2. So that kind of classic degrees of freedom that we've been using in many of the problems. Okay, so we have, under the condition where you have small sample size, you're doing hypothesis testing for the difference between 2 means. We assume the population variances to be the same. We have this test statistic formula and this degrees of freedom for that test statistic formula. So when you go to look up your critical value, you will use this degrees of freedom. All right, so test stat, degrees of freedom, when you go look up your critical value, that's pretty much all you need to worry about that changes when you're dealing with a small sample size scenario under this condition. What happens, however, when this condition is not true? So when we say that the population variances are not equal. Well, in that case, the test stat changes a little bit. We still have t, we still have the top part being identical, being the same, but down here, this bottom part will change. So it'll be just S1 squared, S sub 2 squared. In other words, the sample variance divided by its sample size, the sample variance for the second group divided by its sample size. So that will be the case, and the degrees of freedom will be this if N1 is equal to N2. So if the sample sizes are the same and the population variances are assumed to be unequal, you can use this formula with this degrees of freedom, and that'll work just fine. However, we have the third case now. So at the first case where these guys were considered to be equal, we looked at that formula, that degrees of freedom. The second case is that these guys are unequal, but the sample sizes are equal, and then you use, this procedure. Now what about the third scenario? The third scenario is that these are unequal, and N1 is not equal to N2. So what happens in that instance? Well, the main change is the degrees of freedom, right? So our test stat formula actually remains identical to the last problem that we looked at. However, we're going to have a totally different degrees of freedom. The degrees of freedom is going to be that new formula called NU or NI, depending on how you pronounce it. Either way, that formula then becomes this. It becomes this part here, this S1 squared divided by N1 plus S2 squared divided by N2, that entire thing squared. So that entire top part squared. And then you have these 2 fractions, basically. So you have the first part here is going to be S1 squared divided by N1, that item here, squared, over N1 minus 1. I'm going to write this a little neater. It looks kind of sloppy. So we're going to say again that it's a fraction here involving S1 squared over N1, but that guy is squared, divided by its degrees of freedom. And then on the bottom here, the next fraction is going to have the same kind of thing. We're going to have S2 squared divided by N2 quantity squared divided by n2 minus 1. So all of that becomes the degrees of freedom for this t distribution. That's a pretty ugly formula, and remember we mentioned last time that when using this formula you want to truncate the results. In other words, drop the decimal part if it turns out to be a decimal. If it becomes 38.7, you just call it 38, right? So that's your degrees of freedom. That's the value you'll use when you go to look up your critical value in your step 5 of your hypothesis testing procedure. This would be your step 4, your test stat, and that covers the 3 unique cases that you'll face during hypothesis testing procedures involving small sample sizes when comparing 2 population means from independent populations.